I'm going to give two talks, giving an introduction to some of the landscape of generalized Kähler geometry. I'm going to try to prepare everyone for the talks. There are two other speakers whose talks are related very closely to mine. So one is my student, Leonard Doppelschmidt, who's here, and who will give a talk building on what I'm going to say. And also there's a talk from Francis Bischoff, who actually is supposed to arrive on Thursday or Wednesday night, and he'll be speaking about something related to what I'm saying today. Okay, but let's start with something that I believe everyone is familiar with, which is Kähler geometry. Okay, so let's begin in the Kähler world. So, so the first thing I'd like to discuss is a point of view on Kähler metrics, which is due to Donaldson. And it forms, it's an important idea at the start of his work on Kähler metrics. So let's say that we have a Riemannian manifold, but with a complex structure, so that it is a Kähler structure. Now, when you have a complex structure which is compatible with this Riemannian metric, you can produce the Hermitian two form, and of course the key condition is that it is a symplectic form, so it's closed. And then locally, a local description of this comes from the dd bar lemma, where we could say that omega is dd bar of a function. Let me call it k alpha on u alpha inside n. So we have a Kähler potential. The metric is the consequence of a single real scalar valued function. And I'm going to write this as d bar of minus I del k alpha, which I'll give the name A alpha. It's a one form. A alpha is a 1-0 form on U alpha. Okay, and this this A alpha is obviously not closed, and it's obviously not holomorphic. Okay. However, if I look at the difference of A alpha and A beta, then this is holomorphic, because of course the d bar of this A alpha is global, and so it doesn't matter whether you take d bar of A alpha or A beta, you will get something whose derivative is the Kähler form. And so we have this holomorphic 1-0 form on double overlaps. Okay, and that is defining a class. In H1, the complex manifold with values in the sheaf of holomorphic one forms. So I'm calling X the complex manifold. And this is the Kähler class. Now, this is, of course, not anything new. It's not really an unusual point of view, but let's now use this to build a new point of view. So what we'll do is we're going to use this A alpha beta, this holomorphic data, we're going to use it to build a new complex manifold. A new complex manifold. And what is it going to be? So what I'll do is I'll take the holomorphic cotangent bundle. You can tell that it's holomorphic because I have a curly T. That's for me what it means to be. That's my notation. So this is the holomorphic cotangent bundle of this open set, and this is the holomorphic cotangent of that open set. I can draw a picture of this over U alpha and U beta. And these are pieces of the holomorphic cotangent bundle. And normally, in order to build the holomorphic cotangent bundle, you just glue this piece to this piece by the identity map and the derivative of the identity map. Okay, but I can use this A alpha beta, which is a holomorphic one form on this region here to glue this to this by using the identity map with a vertical translation. So these would be glued like this. So the gluing map is that if I take xp in t star alpha beta, I'm going to glue it to xp plus a alpha beta of x, and this will be inside t star beta. So I'm gluing this to this, but with a vertical translation. So this is a cocycle. So we obtain a new manifold, which I'll call Z. The new manifold is just all these little pieces of the cotangent bundle, T star U alpha, with this identification, XP is identified with XP plus A alpha beta of X. Okay. So Z. What is this Z? Well, what did I build Z from? I built it from these pieces, which are vector bundles, but I glued it by a transformation, which is not a linear map, it's a translation. And therefore, this is no longer a vector bundle, but an affine bundle for the action of the cotangent bundle of X. So that means that it's no longer a vector bundle. Actually, the zero section, maybe the zero section is here, and the zero section is not preserved. Right? The zero section is not taken to the zero section. It's actually lifted. It's vertically translated. And so we don't have a zero section. But you could certainly act on these pieces by vertical translation, and that commutes with this identification, and so therefore we get an affine bundle. So this is called the, sometimes called the twisted cotangent bundle. That's one thing about it. The other thing is that the gluing maps preserve the canonical holomorphic symplectic form, and therefore Z inherits holomorphic symplectic structure. So it is a holomorphic symplectic manifold. Of course, that comes from the fact that the A alpha beta is closed, and so that means the vertical translations are symplectomorphisms. Okay. And so this means that we have incorporated the Kähler class in the construction of a holomorphic symplectic affine bundle. So the Kähler class is encoded by this particular complex symplectic manifold. Okay. We used only the information of the Kähler class in order to build this thing. Okay, so that's the interpretation of the Kähler class that Donaldson suggests to us in 2000, in the year 2000. Now, if that's the Kähler class, then what are Kähler metrics in that class? So what are Kähler metrics in the class of omega? And for this, we just go back to the construction. So you see that see, originally we had these A alphas, and these A alphas were only locally defined. And their difference is this A alpha beta, which I used to glue to produce Z. So these used to be only locally defined, but because I made a space from the discrepancy, now these things become globally defined in that space. So the A alphas now glue to A betas. So what I mean is that if I look at the graph of A alpha inside holomorphic cotangent bundle of U alpha, and if I look at the graph of A beta inside holomorphic cotangent of U beta, one is glued to the other by this map, by the construction. And so therefore, the graph of A alpha is global. It defines a submanifold of Z. Here's Z. Here's the projection to X. Z has fibers. Okay, but it doesn't have a zero section. But instead of having a zero section, it has this section, this graph, which I call L. Now, these the important thing is that these A alphas, they are not holomorphic. Right? And therefore, this submanifold is not holomorphic. See, this is the warning. But L inside Z is not holomorphic. It's C infinity instead. And the key property is that we can recover the Kähler metric from this submanifold. The Kähler metric omega from L in a very nice way. How? Well, we need to look at the ambient space. The ambient space, remember, is holomorphic symplectic. And therefore, this holomorphic two form, I can restrict it, I can pull it back to L. This is the inclusion map of L into Z. And I can pull back omega Z and get a two form on L. And the claim is that this two form is a way of recovering the Kähler metric. Okay, why? Well, okay, what happens if I take this symplectic form, holomorphic symplectic form, and I pull it back to this real submanifold? Well, what am I doing? Locally speaking, this holomorphic symplectic form is just the canonical symplectic form on the cotangent bundle, the canonical symplectic form. And I'm taking that canonical symplectic form, okay, and I'm restricting it to the graph of a one form. So whenever you take the canonical symplectic form on the cotangent bundle and restrict it to the graph of a one form, what you get is the derivative of that one form. So this is equal to the derivative of A alpha. This is on U alpha, that's what its value is. Okay? But the derivative of alpha, right, has two components, del and del bar. The del part is zero because A alpha is del of a function. So the only thing that remains is d bar of alpha, and d bar of alpha is omega. And so this tells us that, number one, we recover, well, maybe number one, maybe the first observation is that this complex two form, when restricted to L, is actually real. Real. And maybe important comment is that it is the Kähler metric. I mean, technically it's the symplectic form, but from the symplectic form and the complex structure, we get the Kähler metric. Okay. So this means that another way of phrasing this, so a rephrasing, is that L inside Z omega Z is what Donaldson called an LS submanifold. Not a very elegant term, but it means Lagrangian symplectic, because it is Lagrangian for the imaginary part of omega Z, which itself is a real symplectic form. And it's symplectic. Sorry, I should write the word Lagrangian at least the first time. It's symplectic for the real part of omega Z. Put this up. That's the first important thing I want to say in this series of talks, is that Donaldson gave us an interpretation of a Kähler class as being a holomorphic symplectic affine bundle. Okay. And an interpretation of the Kähler metrics in that class as being LS submanifolds. Actually, it's not just a submanifold, but it's a section. The C infinity section of pi. And so you have this very beautiful picture that the Kähler metric is just this Lagrangian inside T plus T, inside T star, inside this twisted cotangent bundle. And if you move that Lagrangian around, you're changing the Kähler metric in the class. Okay. And maybe the the beautiful outcome, or the kind of remarkable fact, so interesting fact, is that this really shows very clearly that that a Kähler metric depends on a scalar function, because it's a Lagrangian submanifold, and therefore it's a generating function, or if you give me a function. So the degree of freedom omega is just a real valued function. Real valued function which moves the Lagrangian L by a Hamiltonian flow. Maybe just to make it as clear as possible, if I have Z, if I have this nice cross section, then you can deform this cross section by a function, right? If I take a function on the manifold, then I can pull it back to Z, and I can take the imaginary Hamiltonian flow. I can take imaginary omega Z inverse df, and produce a vector field, let me call it V, and the flow of V takes omega to omega plus I dd bar of a function. Moving the Lagrangian submanifold, maintaining the fact that it's Lagrangian. And if you choose the function small enough, then it will maintain the fact that it's symplectic, which is an open condition.
Okay, I guess somewhere like in these formulas in the upper right, you're sort of pulling back to X. You're sort of pulling back by the graph parameterization to say it's equal to omega.
Oh, yeah, it's a section. So you're right. I should put that, this is pulling back to L, but really L is identified with M just by projection.
Yeah.
And so
using the section gamma. So
yeah, using the section to identify it with the base. Thank you.
And why are you taking a function on the base manifold instead of just a function on the total space?
You could indeed take a function of the total space and move L around. That's true. The advantage of taking a function on the base is just that the vector field will be parallel to the fibers, and so it will be easy to track that section because it just moves. It's actually deforming not just the submanifold, but even the map that defines the section, and it gives another section. If you were moving horizontally, then you'd have to calculate what the corresponding section is.
More things, or like if you don't require it to be exact, but just like, is there a difference between Hamiltonian and symplectomorphism? That's kind of the question.
Not really, because you can, whatever you get is always going to be a section. And so you can always look at the final section and just take the difference and see that it has to be.
So since Z has a canonical holomorphic symplectic structure, does it also mean that it has a canonical hyperkähler structure?
No. The existence of a hyperkähler structure on a holomorphic symplectic manifold really depends on the fact that that is a compact holomorphic symplectic manifold in order to use Yau's theorem. And here, this is definitely non-compact. And so there's some famous results, like there's results of fakes, Birta fakes, and Dimitri Kaledin, which shows that even on a Riemann surface, the holomorphic cotangent bundle is not hyperkähler in general. Yeah. Okay, so this is really the key thing. So in order to understand the rest of my talk today, and for the next talk, and for Leonard's talk, and for Francis' talk, these four boards are the only really necessary ingredient. So if you have questions, now's the time.
Is there anything special when the manifold is scalar geometry? If the canonical is triple, is there anything special about the geometry?
So far, there's nothing unusual that occurs. It's still the same idea that the Kähler metrics are given by these sections, but I think that you'll see the appearance of the Calabi-Yau structure in Leonard's talk. So the point is that this is a little bit of an unusual way. Okay, so I should say two things. So the first thing is that Donaldson liked this approach because it makes the Kähler potential into a global thing. The Kähler potential, right, normally is only local, but now that we have interpreted it as a Lagrangian, then that's the Kähler potential, really. Or you should think that maybe the Kähler potential is just a means of moving that Lagrangian around. Okay. The second thing is that what I'm going to talk about for the rest of my talk today is generalized Kähler metrics. Okay. And the cool thing is that in order to understand generalized Kähler metrics, okay, this idea that we have a nice form which is closed, and which we can use the D-Dubar lemma to extract a function, and so on. This part of the argument fails for generalized Kähler structures. But it turns out that this picture of the metric being determined by a Lagrangian submanifold, that persists. And that's the thing that took us quite a while to understand. Erase.
So what kind of degeneration of the metric does it mean if the Lagrangian is becoming vertical?
Good question. I don't have anything good to say about that, but it's a good question. Yeah, interesting idea.
I've got another question.
Yeah.
So, to what extent can you work this out when it's the complex structure is not necessarily integral? Is there something really necessary to have complex coordinates, or this picture kind of?
Well, so you could investigate whether anything like this is true. The only problem is that you wouldn't have this holomorphic symplectic manifold. And so maybe that would fail to be closed or something, but it's not even a complex manifold. So I don't know, I haven't thought of that.
You wouldn't have the potential to glue in.
Correct, you wouldn't have Darboux coordinates, you wouldn't have potential. So, and that's expected, right? For a non-integrable Kähler manifold, it shouldn't be that the metric is determined by a function. But But I have a prejudice against non-integrable things. So.
If you had a special type of Kähler metric in the class, like Kähler Einstein or Calabi-Yau, does that mean a special type of Lagrangian submanifold?
Okay, so that's a very good question in the context of the talks that are being planned here. So, so what Jason was just asking about is, well, okay, we know that in a Kähler class, there are some very famous results, like Yau's theorem, for example, which indicate that among the various LS sections, there could be a distinguished, very special one that has some kind of minimization property, or that is, the ultimate section that you really want to consider. Now, you might be tempted to think, oh, well, maybe if this is Lagrangian, then maybe the special ones are the special Lagrangians. Okay, but I just want to emphasize that this space Z does not have a metric. It is a holomorphic symplectic manifold. It's very important that it does not have a metric structure. Okay, the metric structure is emergent. Okay, in the sense that it emerges from the fact that this is holomorphic, this is a complex manifold, and that we have we have a symplectic form on L. So I just want to kind of I'm used to this by now, this geometry, but I want to explain how. I just want to point out how bizarre this is, right? That this is a holomorphic symplectic form, and therefore it's a 2-0 form. But when I pull it back to L, I get a Kähler form, which is a 1-1 form. That's strange, right? Why is this occurring? Well, it's because this is not a complex submanifold. This is a smooth submanifold, and we pull back a 2-0 form to it, and it becomes 1-1. Strange, but true. Okay. So the question of where are the special sections, that will be determined by certain interesting functionals that can be defined in a context like this, and which Leonard will talk about. Okay. But it isn't something that is, let's say, some obvious condition on the Lagrangian like being special. Okay, so let me give just a really simple example. What's the simplest? What's everyone's favorite Kähler manifold? Well, my favorite is P1 with the Fubini-Studi metric. So in this case, what you can do is, so Z, this Z space is going to be a deformation of the cotangent bundle of P1. And well, there's only really one interesting deformation of T star P1, and it's the deformation to an affine quadric. The quadric is x squared plus y squared plus z squared is equal to 1 inside C3. So we have an affine variety, affine algebraic variety inside C3, quadric hypersurface, and the holomorphic symplectic form is, you can write it in the following way. You write it as dx wedge dy over 2z, which is a singular form on C3, but if you pull it back to this thing, it's not singular, and it's a holomorphic symplectic form. Okay. And so this affine quadric, together with this holomorphic symplectic form, this is the Kähler class, believe it or not. This is the Kähler class. This is determined by and determines the Kähler class in H1, P1, omega 1. Okay, and in order to tell you the precise metric in that class, I need to provide a section of this bundle. And the section has to be Lagrangian for the imaginary part and symplectic for the real part. Well, an easy way of doing that is to use the real structure on this complex manifold, the real structure being taking x, y, z to x bar, z, y bar, z bar, right? And the fixed point set is, I shouldn't have drawn it like this. I should have drawn it like this, let's say. It's a two-sphere sitting inside there. So the real locus is an S2 embedded inside this quadric. And it is LS, And it is the Fubini-Studi metric. So the Fubini-Studi metric is just the real locus inside a affine quadric. Interesting idea, but that's what this point of view says.
Can I ask a question? When you actually refer to L, you said a real submanifold, and I was actually going to ask you, is it real submanifold in the sense that it's a fixed point of a conjugation? Always?
Not necessarily, no.
Yeah.
In fact, the Z space doesn't necessarily have these additional symmetries like a real structure or anything like that. This is just, we're just lucky and a nice really study metric.
Real submanifold, really.
Yeah, actually, if you think of usual Kähler, so yeah, I think that's accurate. So yeah, these LS submanifolds, they do behave a lot like real submanifolds, totally real submanifolds. They do behave like that, but in general, they're not going to be totally real. Okay, so
do these spaces sets arise via the formation of the holomorphic cotangent always, so you can always put it in a family or something?
So in the Kähler case, when we're trying to analyze Kähler metrics, a la Donaldson, then yes, you take the cotangent bundle and the Kähler form. You could think of it. See, you have a class in H1 P1 omega 1, right? Okay, so what you do is you pull this back to Z. And you get a class, there's a map, a pullback map, which goes to H1 Z omega 1. And then you use omega inverse to convert this omega 1 to T, H1 Z T. That is how you deform Z. That's the deformation class of Z. So there's always an available class for deforming the holomorphic cotangent bundle to what they call the twisted holomorphic cotangent bundle. And these fit into a nice a nice algebraic family of complex symplectic manifolds. And that's the holomorphic, that's the twisted cotangent bundle construction. And that's the one that you have to use to understand Kähler metrics.
And is it always the case that Z doesn't have any compact complex manifolds? Because here is the case, right? You have
I don't remember if it always, I don't remember if it's always like that, but I have a feeling that it is always affine. Yeah, but I don't remember. I don't recall. You have to look up. If I wanted to find the answer to your question, I would look for the Joannou construction, and it's explained in that. I don't remember the details. Okay, so what I've described is this viewpoint on Kähler metrics, and I've given an example. Now I'm going to explain. Without talking about generalized geometry, I'm going to explain a way in which this entire picture can be deformed. So now we go to a deformation of the entire picture. And this deformation is governed by holomorphic Poisson structures. Okay, so when I say holomorphic Poisson structure, what I mean is that I have a section of wedge 2 T10, which is holomorphic, and which satisfies this condition, namely that the Schouten bracket of it itself is 0, so it defines And usually I'll write this as in terms of the real and imaginary parts. So this is a holomorphic Poisson structure. P and Q are real Poisson structures. And because this is holomorphic, P is just obtained by taking Q and pre or post composing it with the complex structure I. And also the Scouten bracket of P with Q is also 0. So a holomorphic Poisson structure is really, it's a pair of real Poisson structures whose quotient is the complex structure on the manifold, which commute with each other. That's really what it is. It's a pair of commuting real Poisson structures differing by a complex structure. So anyway, these are not as plentiful. You know, they're more plentiful than, let's say, holomorphic symplectic structures. They exist, for example, on CP2, on many Fano manifolds, but they don't occur on certain special classes of manifolds. Like, for example, on compact Calabi-Yaos with fundamental group 0, trivial fundamental group, these don't exist. And so this deformation that I'm about to describe is only available for a certain subclass of Kähler manifolds, namely the ones that admit a holomorphic Poisson bracket. Okay, so let me just give an example of this. And I'm going to take a really simple example. I'll take C2. So C2 with coordinates Z1 and Z2, or actually I'll use X and Y. And I'll take the Poisson structure to be this one, X d by dx, wedge Y d by dy. This is, and I'll multiply it by t, just a constant. So what this looks like is that you have C2, and the Poisson structure degenerates at xy equals 0, so it degenerates on the coordinate axes. Okay. And so the picture is usually just need 2 colors, but I only have 1 for right now. There used to be a red, but it got pulverized. It's okay. A bit of an orange. Okay. So this Poisson structure degenerates at x equals 0 and y equals 0. So a Poisson manifold always has symplectic leaves. So one of the symplectic leaves is all of this. So it's an open, dense symplectic leaf. The symplectic form, which is the inverse of this, blows up here, right? So the symplectic form, if you were to invert this, it would look like T inverse x, T inverse d log x wedge d log y. So this thing blows up along the xy axes, and the symplectic leaves here are just the points. So we have infinitely many symplectic leaves, which are points, and then we have a big symplectic leaf, which is the complement of the axis of this singular curve. Okay, this is what the Poisson structure looks like. Oh, thanks a lot. Okay, and okay, and so this is the data that we need to deform the whole picture that we've discussed so far. So how do we deform this? So Z, I'm going to produce a new Z, and so what would Z be? In the Kähler case, it would just be the twisted cotangent bundle, a deformation of the cotangent bundle of C2. And there aren't really, that deformation is just C2 again. It's just the cotangent of C2. and I'm not actually going to deform the complex structure. So this is just going to be the holomorphic cotangent of C2, which is C2 cross C2. Or if you prefer, C2 cross the dual C2. That's what the Z will be. Nothing interesting happening on Z. Okay. The coordinates here will be X, Y, and A, B. So these are the momentum coordinates on the cotangent fibers. Okay, so the usual projection map from the cotangent to the base would just take this point to X, Y. But what we're going to do is to deform pi. It seems like a strange thing to do, but the cotangent bundle projection is going to be deformed, and we're going to deform it to get two maps. We're going to get a pair of maps, S and T. And the maps are as follows: X, Y, A, B goes to, okay, so let me write the formula and then I'll explain where it comes from. So e to the minus t by multiplied by x, and y is left alone. And this one, x is left alone, and we have e to the minus t ax multiplied by y. Okay. So what's happening is that depending on the value of the momentum b, okay, b gets exponentiated, b multiplied by y and t gets exponentiated to get a non-zero complex number, and we rescale x, but we don't do anything to y. And here we rescale y and don't do anything to x. Where does this map come from? It basically comes from a Hamiltonian flow by this Poisson structure. So, for example, if I take the function y, and if I look at the Hamiltonian flow of y will produce, to get the Hamiltonian flow, you just take the derivative of y and you hook it into this. That cancels out the d by dy, and what you end up with is txy times d by dx. So for example, if you look at the Hamiltonian flow of y, you get txy, ty x d by dx. Now, this is the Euler vector field in the x coordinate, which rescales x. And this is just a coefficient in front of that rescaling. So if we were to exponentiate this vector field for time b, that's what we would get. We would get a rescaling of x by this complex number. Okay, so this is the Hamiltonian flow of y. Okay? And this is the Hamiltonian flow of x. Okay, so what we're doing is we're incorporating the Poisson tensor, the Poisson structure here. Okay, we're incorporating it to move the points on the base, which is in a holomorphic way. And that's something that we don't usually do in Kähler geometry. We don't have a holomorphic Poisson structure. Okay, so in fact, we can think of xy AB as an arrow from the source S, let me just call this point Z, S of Z, to the target T of Z. So let me erase and let you observe that. What we've done is we've created two maps deforming the simple projection. And we're going to view every point in the cotangent bundle as if it was an arrow, which goes between 2 points of the base. And those 2 points are S of Z and T of Z. Just this point is an arrow which goes from e to the minus t by x y to e to the minus 2x e to the minus t a x y. Okay. And the purpose of this is the purpose of this space and these two maps, okay, what you should think is that this space is now encoding, roughly speaking, it's encoding all possible Hamiltonian flows that you could get. Because it's telling you that by doing the Hamiltonian flow of y and the Hamiltonian of x, and if you just look at where you can get by those Hamiltonian flows, okay, you can, so they're parametrized by this space. So in a way, Z parametrizes, roughly speaking, all possible Hamiltonian flows applied to the points of C2. And this thing is called, it has a name. So it's one of the primary objects of study in Poisson geometry, and it's called the Weinstein symplectic groupoid. Of C2 pi, C2 sigma. And it's a topic of much research, and it so happens that in this case, with such a simple Poisson structure, we can write the Weinstein symplectic groupoid in a very explicit way. And I should say, the unexpected thing, when I describe it in this way, when I describe it as the parametrized family of all these symplectic form, all of these Hamiltonian flows, the thing which is maybe not so obvious is this fact, the fact that it has a canonical symplectic structure. So the symplectic structure on Z do I go until 11 or until 1050?
At 11.
11, okay, thank you. So symplectic structure on Z is as follows. Okay, what you do is this. So this is the cool thing about the symplectic groupoid, that we look at this symplectic form. Well, this is a symplectic form on C2, but the problem is that it's singular. Okay. But look at the maps that relate this space with this space. Notice that we have exponentials here. So it turns out that if we take this T inverse d log x, d log y, and if I pull it back, I'm sorry that I used T for this number here, and also for this map. Forgive me for that. If I take T pullback of this, and if I take S pullback of this, you can amuse yourself by computing these pullbacks, and what you get is the following: dA wedge dx plus dB wedge dy. This is a holomorphic symplectic form on Z. Z. And not only that, but if you take that symplectic form on Z and you invert it, you'll get a Poisson structure on Z, which is non-degenerate. And if you push it down by these two maps, if you push it down by T, you will get the Poisson structure we started with. And if you push it down by S, you will also get, with a minus sign, the Poisson structure that we started with. So in a way, you can think of Z, omega Z, as a symplectic resolution of of the Poisson tensor. So the picture is the following: that we have C2 with its Poisson tensor. The Poisson tensor has this nasty behavior, nasty geometric behavior with these nasty degenerate symplectic leaves and so on. So what we do is we produce a C4 Z space, we call it Z. And the geometry up here is totally regular. It's just a symplectic structure, holomorphic symplectic structure. And what happens is that we have two maps, the source and the target map, down to the base. And the source map has fibers. It's a submersion, so it has nice submanifold of dimension 2 fibers. And the target map also has fibers. And the point is that these two maps are Poisson maps from this non-degenerate Poisson structure to this degenerate Poisson structure. Okay, and so you can think of this as a symplectic resolution in the sense that you resolve the nastiness of the Poisson tensor. Okay, but the interesting thing is that because of this interpretation of this space as defining Hamiltonian flows, it turns out that this space, this geometric manifold, it has the structure of a groupoid, so that every point in this space could be viewed as an arrow that goes between the source and the target. So you could think that there's a composition law here, right? So in other words, the composition law, it kind of looks like this, that if you have a point, so first of all, there's an embedding of the base as identity arrows, and those are when you take A and B to be 0. So this is the so-called identity section, X, Y, 0, 0. Okay. And anything else can be thought of as an arrow that goes from one point to another. And then you could compose it with another element, as long as the source of this element is the same as the target of this element. And then you could compose them, let's say if this is H, and you could compose them to HG. So there is a H composition. So this is the reason why it's called a groupoid. Okay. So what have we done so far? So we've just taken a complex manifold, which is C2. We've equipped it with a Poisson structure, and we've desingularized this Poisson structure into this bizarre double-dimensional space, which is a holomorphic symplectic manifold. And the idea is that we could execute the same idea. So we could, for example, take omega, which is dA wedge dx plus dB wedge dy. These are Darboux coordinates, x, y, and AB. And what we could do is we could choose a C infinity cross section. And now we have to choose a cross section to both the red and the blue foliation. So we need to choose a C infinity cross section of S and T. These are called bisections, which is a really bad term because it makes it seem like you're cutting something in half, but it's not. It's not, you're not bisecting anything. It's just two sections. They could have called it a double section. Okay, and let me just draw these in just to. So this is a section of both of the maps from the AB XY space down to the XY space. And and how do I describe this C infinity cross section? Well, I want it to be LS with respect to omega z. So I want this thing to be just like the Kähler metric in the Donaldson picture. So one way to do that is to let L be the graph of minus I d bar k, minus I del k, where k is some C infinity function of x and y. And if we, right, and so in other words, we would have that L is defined by the conditions that A is minus I del d by d x of k, and B is minus I d by dy of k. We could take k, for example, to be, let me take a familiar one. Let me take k to be 1 over 2 pi log 1 plus norm x squared plus norm y squared. So this is just, I could have chosen anything, but I chose this particular C infinity function. And this will lead to L being a LS bisection for T sufficiently small. There's a condition, I could write it explicitly how, because after a certain point, if T is too large in norm, then the S condition is going to be violated. So in other words, when we restrict this holomorphic symplectic form, what we're going to get is we'll get a two form F, which is a real closed two form on the manifold M. And in the last minute, I'm just going to tell you what this produces. So this is what you obtain from this deformation. What you end up with is this two form F. So unlike the Kähler case, F is not type 1,1, but rather F is equal to, if I combine F with the complex structure, what you get is a metric, but it also has a skew symmetric part. And this is what we call a generalized metric. On C2. So now we get a metric plus a B field on C2 from doing the same thing that we did in the Kähler case. Okay, but we also get a pair I plus and I minus complex structures I'm just going to identify MC2 with this cross section L, like I did before, but I'm going to get a pair of complex structures on M because you see, this cross section is smooth. It's not complex, it's not holomorphic, so it doesn't inherit a complex structure as being a submanifold. It inherits a complex structure because of the fact that it's transverse to these holomorphic foliations. There are two such foliations, and so there will be two complex structures induced on L. I call them I plus and I minus. The foliations, S and T. Another, okay. And it turns out that if we combine the metric with these complex structures, get the Hermitian forms omega plus minus, these are not closed, but they satisfy the condition that dc plus omega plus dc minus omega minus is equal to 0, and dc omega plus minus is equal to 0. And this is exactly the condition, this is exactly what is called generalized Kähler geometry. Which was the geometry discovered in 1984 by Gates, Hull, and Rocek as the general n equals 2,2 background, supersymmetric background for two-dimensional sigma models. So okay, and maybe the last thing I should say is that this Poisson structure, is the Hitchin Poisson structure, which is part of this this generalized Kähler geometry. Is understood by Hitchin that it determines the holomorphic Poisson structure. So what I'm trying to describe to you is that the idea that a Kähler metric is a Lagrangian inside this holomorphic symplectic space, it continues to be true in this deformed version where we use a holomorphic Poisson structure to deform the geometry on the base as well as the nature of the holomorphic symplectic manifold. Okay. And the funny thing that occurs is that the standard projection to the base splits into two projections. And this goes along with the idea of Rocek that he told me, 10 years ago, that he thinks of these things as schizophrenic Kähler manifolds. And there's two different complex structures, and here we see them as two foliations, two versions of the cotangent bundle projection. Okay, and so this is a kind of, once we understand this picture, once we see that you can obtain them by deformation, it allows you to write down a lot of generalized Kähler metrics just by picking a single function and taking derivatives in a Darboux coordinate system for the holomorphic symplectic Weinstein groupoid. Okay, I'll stop there, and thanks for your attention.
Any questions or comments? What's the intuitive meaning of the composition law on the groupoid?
It's simply that, you see, because we have a holomorphic Poisson structure, we have the ability to do Hamiltonian flows, and then you can just compose those. You Hamiltonian flow from one point to another point, and then you Hamiltonian flow to another point with a different Hamiltonian, and so on. That's all. That's all that it is. That's the reason that the holomorphic symplectic. That's why the Weinstein groupoid is a groupoid.
In terms of coordinates, is that just addition of the A and B part of the points?
Actually, so it turns out that if you have x, y, a, b, and you have x prime, y prime, a prime, b prime, right? You need to translate them so that they lie over the same point. So you need to apply Hamiltonian flows so that they lie in the same fiber of the original cotangent bundle. then you could use the original addition in the cotangent bundle and you'll get the correct answer. But in general, what you would need to do is just compute with the formulas that I explained before, just compute a composition. And in those coordinates, it doesn't look like just A plus B. It involves these modification of flows. You have to flow them together, then add, then you get.
Yeah. Oh, yeah. I was just curious, right? So there's these like different examples of generalized Kähler taking Kähler and deforming by a Poisson tensor.
Yeah.
So is this whole picture sort of smooth along such a family?
Yeah. So there's this operation that you're referring to, which we call the flow construction, and there's many versions of it depending on what setting you're in. But that construction boils down to the following thing: that just like in the Kähler case, okay, what I could do is take a function on the base, a smooth function on the base, and pull it back by S or by T. You have two options. You pull it back, you take the Hamiltonian vector field of that, and you move this Lagrangian by that. Okay, so you can see that if you use S to pull back the function, then L will move along the fibers of S, and therefore the projection to the base will not be affected by S. But when you project it by T, you're going to get a different complex structure. So depending on whether you pull back your smooth functions from the right side or from the left side, you'll move that Lagrangian either this way or that way. Okay. In either case, it's a Hamiltonian flow. So all this geometry will be preserved, and you will get a flow construction. You will get a deformed GK metric. The metric will change, just like in the same way that we added dd bar of a function in the Kähler case. That was just an unambiguous flow up the cotangent bundle. Here we have two possible directions, and the difference is simply whether you prefer, in studying the deformation of this geometry, it's simply the question of whether you prefer to keep I plus fixed while you move I minus, or whether you keep I minus fixed and move I plus. It's simply that. That's the only difference of whether you use a function from one side or from another side.
But somehow, like everything on the total space is just converging nicely, like as you turn the Poisson tensor off.
Sorry. So yeah, I was describing the case where you keep the Poisson structure unchanged. Right. If you keep the Poisson structure unchanged, then the ambient geometry remains unchanged. Okay, now what you could also do is you could study a deformation of Poisson structure. The symplectic groupoid would deform, and you have a family of symplectic groupoids. And then you could take a Lagrangian section here, and you could push it horizontally to the nearby symplectic groupoids. And there's a version of the flow which corresponds to that, which I just described. Yeah. But that requires you to understand the degeneration of the symplectic groupoid to the commutative one. Right. Yeah. And that is a smooth family of symplectic groupoids. Yeah. Yeah.
Yes.
What kind of properties of the homomorphic Poisson structure are the essential? Is it like because it's log symplectic or the integral bond?
No. The only real thing that's important is that you. So there isn't any. No, there's no requirement. Yeah. So the theorem, I didn't state the theorem, but in my paper with Francis and Maxime, we proved that generalized Kähler structures of what is called symplectic type are in one-to-one correspondence with this bisection geometry. So it's a one-to-one correspondence between generalized Kähler metrics in the standard case, in the standard sense, and this type of geometry. But I should write one thing, which is that we're assuming that I plus I minus, this tensor is invertible. Okay, this is the so-called symplectic case. And I'm going to say more about this in my second talk. Okay, but we in the first paper, we are assuming that I plus I minus is invertible in order to get the one-to-one correspondence. And it took a lot of thought and effort to extend it to the most general case. And that's what I'll explain in my second talk. In that case, we unfortunately cannot do simply with a symplectic groupoid. We need what's called a Poisson groupoid to understand that case.
So it's just a question to avoid a possible misunderstanding. So these structures I plus I minus are biholomorphic to the complex structure on the base using SNT, or how you define them?
Okay, so the way that they're defined is like this. So, okay, so yeah, so that's correct.
Yeah. Okay.
That's correct.
But just continue, because I thought there was an example that you guys had with like the surfaces of the non-generic ones that you somehow deform and keep one still the non-generic one, but the other one that minus would become a generic one.
Right.
I kind of thought would fit in this framework. Does it?
Yes. So right. Yeah, so the it fits into this framework in the following way, and I'll try to keep it as brief as possible. Okay, so do I have some space somewhere? Okay, here. So so I was describing the case where you have a complex manifold, and you have this, this groupoid over it. This. Now, sometimes for generalized Kähler structures, the two complex structures I plus and I minus are not isomorphic. They can be non-isomorphic complex manifolds. So that means that there would be another x prime, I prime. And the idea is that in such a case, we cannot have a single groupoid over a single complex manifold. It turns out that what we need is something that looks like a groupoid, which has a map here and a map here. And this is called a principal bundle for this groupoid. So this groupoid acts on this space as a torsor, like a principal bundle, over this base. Okay, so it's something which is almost identical with the groupoid, but which is really a principal bundle. It's a torsor for the groupoid. And this thing has the bisection. And then by the same method, you identify that one of the complex structures is the identification with here, and the other complex structure is the identification with this. But this is a holomorphic symplectic manifold, just like I explained. It's just that it cannot be over the same space, that the two maps go to two different spaces. Okay. That doesn't occur in the example I gave just because it's C2, and yeah. But I'll try to say more about this.
Yes, one quick question. Is this somehow related to a generalized Kähler structure on the Hopf surface, or this is not the case? Or this is just a non-compact example?
So you mean this particular example?
Yeah. Yes, just because the generalized Kähler potential that you got looks very similar to the one for the Poisson entry.
What Mario asked was whether the GK structure on C2 with this type of geometry, whether it is related to the GK structure on the Hopf surface, S3 cross S1, because you could quotient this by a rescaling map and get down to the Hopf surface. So the answer is yes, but it is related. But what you'll find is that the rescaling map will introduce a three-form flux. If you really want to go to the quotient, you need to introduce a three-form flux, and so you will get a relation with the Hopf surface. Yeah, but actually, the important thing is that kind of an interesting thing is that the Hopf surface example does not satisfy this this condition because it doesn't have a symplectic structure. So yeah. What I said doesn't apply directly, but through this quotient construction, you could relate it to the Hopf surface. You get a lot more questions when it's not on Zoom. Zoom is terrible.
Okay, let's
Okay,
take one question.
Thank you.